Yeah, we have a lot of physical quantity. In this section, I wrote some physical quantity. Apart from this, there are more physical quantity that I will be writing. Here, our focus is on the discussion of how to find a dimensional formula and what are those dimensional formula of those physical quantity that we are going to write. Okay, here as you can see I wrote 10 physical quantities, and here we will find all those dimensional formula we will write here of these physical quantities, as well as we will write SI units. We will not ignore it at all. Okay, it will not be ignored. First of all, we will see what do we have physical quantity, then we will find SI unit, then we will write dimensional formula for those physical quantities. Clear? So first we have area, and you know that unit for this area is nothing but just meter. Meter. But hold on, not meter. Meter and square. Just meter is a for displacement, for distance. Okay. So unit for area is a meter square. You know that yes, it is a unit for meter square. In details, we will explore it. Okay, nothing will be ignored. In this section, we will write physical quantity. In this section, we will be writing SI unit of physical quantity, and in this section, dimensional formula will be written. Okay, will be. So we have written unit of SI unit of area, which is meter square. Now, what should be dimensional formula for this area? You know that this is nothing but just length. So we don't have m, so m exponent would be 0, because we don't have m, we don't have mass. M, which means mass, L length, and time. Here m, meter, which means length. Here we are measuring length, isn't it? We are measuring length. So meter is just length. Centimeter is just length. Millimeter is also length. All these are different units. And here all these are representing that yes, we are measuring a length. Clear? So length is how much? Exponent is a 2. Exponent is a 2. Hold on. It started not working. Are you feeling bored? Worrying? Are you feeling worried? It's not fault. It's not my fault. Yeah, it's not my fault. Look at our T. We don't have time for area. So here T would be nothing but 0, and we round it by using a square bracket. Open a square bracket and close the square bracket. This is complete dimensional formula for area quantity. So it is what? M0 L2. This is how it is read. M0 L2 A0. Clear? For volume, unit is SI unit is 3 m cube, m cube, m cube. Now here L, exponent of L is what? 3, and M is 0. M is 0, L is 3, and T is 0. T is 0 because we don't have time. M is 0 because we don't have mass. In this we have only length, and exponent is a 3. Clear? Exponent is a 3. Now next we have mass density. Mass density. I think it should be kg m cube. I think so. Can you just look at over here? Tell me mass here. We have mass density. kg m cube. Yeah, I am right. So next we have what? Next we have mass density. So you are crystal clear from this word mass kg per meter cube. Here we have density. You know that density is a three dimension. It has a three dimension. That's why three exponent is coming over here. kg is a mass, so mass is one, and here exponent is one. That is what we are saying. Exponent is one, and here you know that one is added, one is added. And here we have length, and this three is a denominator. For denominator we write exponential negative. So L is minus 3 and T is nothing. This is complete. Here we are saying M is 1. M1, L minus 3, T 0. That is how it is written. That is how it is written. Even you can write this one, okay, for your satisfaction. M1, L2. Now next we have velocity aspect. Both are same. Just the difference is that one will provide a direction, but another will not provide a direction. Here a speed does provide what it provides velocity provides direction, but a speed always does not provide direction. But here, as we know that unit for both is the same, meter per second. Meter per second. Meter per second. Here we have a length time, but not the mass. So for mass would be 0, L is 1 and T is 1. This is complete dimension formula. Now next we have acceleration. You know that. Just s raised to power 2. That's it. Meter per second square. Meter per second square. This is the unit of for acceleration. You know. Okay. Meter per second square is just acceleration. Remember, this is not boring points. Okay. Here we will understand it heartfully. Okay. Because it will help us in each chapter of 11th standard and 12th standard. Okay. All this will be linked. Don't think that all these are useless. No, don't think like that. All these are useful. It will help us in each chapter of 11th standard as well as 12th standard. You will see. All these are very small important points that we need to understand in details as much as we can understand. Okay. Look at here. Acceleration. Here unit is meter per second square. Difference both between this and this is what? Here is a square, here is 1. Here exponent is 1, here 2. Right now I am not going to into too much details about acceleration, about all this quantity. Just our focus is on what is the SI unit of this physical quantities and how to write the dimension. What would be dimension formula for this physical quantity? That is what our focus would be on this. Okay, on this. So here, length is 1, m is nothing. Length is 1 and t is 2. M0, L1, t. Hold on. Here, this is in denominator. So it would be minus 2. M0, L1, t minus 2. Okay. It is complete. Next we have force. It is Newton. Yeah. This is Newton. You know that force. This is what Newton. It is what Newton. Okay. This is what you will have to do because because a lot of times newtons will come. So the SI unit for is what? Newton. Newton. Now here, look at over here. We selected some physical quantities that is important for this uh, for this topic, mechanics and motion. Mechanics and motion. All these are those physical quantities that are important for this mechanics and motion. Okay, we have separated some physical quantities. Now look at over here. Newton. Remember, the dimensional formula for this is what? M1, L1, L1, and here M1, which means kg meter per second. Kg meter per second square. Okay, kg meter per second square. This. Here you can say kg meter per second square. That is what you are saying. Newton or this unit. This is a unit for this force. Clear? Clear? I brought this with the help of this dimensional formula. I cannot say that this is wrong. No, this is right. I can confidently say this is the evidence. Is this dimension is evidence. Now for next week, one point here I would say, brother, that remember this force. Okay, a lot of time this will come. That's why I say, just for fluency, you will have to keep remember in your mind. M1 L1 T raised to power minus M1 L1 T minus 2. That's it. Otherwise you can say kg meter per second square. Kg meter per second square. Now next we have impulse. Impulse is what? SI unit for this word Newton into second. Newton per second. Impulse. Newton per second. Newton per second. Newton per second. I think not per second, but Newton into second. Into second. This is the SI unit for impulse. Here we know that. Here you can see force is coming in for impulse. So rather than writing from scratch, we can write only dimensional formula for this, and then we will have a second. We will apply T for second. So here we know that dimensional formula for Newton is nothing but just this N1 L1, and here already we have 1 and here we have minus 2. So 1 minus 2 will give you minus 1. Exponent rules. I applied exponent rules. Okay. T minus 1. It is a dimensional formula for impulse. What did I do? I just wrote this dimensional formula of force, and then just I saw there's a second. Here it is giving you positive exponent, and here we have already negative minus 2 exponent. Just we added. That's it. M1 L1 T raised to power minus 1. M1 L1 T raised to power minus 1. M1 L1 T raised to power minus 1. So remember SI unit for impulse is Newton into second. Next we have work joule. Next we have work joule. It SI unit of work or energy. You know that this is just joule, or it can be kg meter square per second square. This is a complete. Here, look at here. Remember, Joule is also unit. Joule is also unit for work as well as for energy. Okay. You can see Joule is SI unit for work and it is also SI unit for energy. Here you have two options. Either you can pick this Joule as a SI unit or this kg meter square per second square. You have two options. This is your choice. Now look at over here. Look at over here. Here we have kg, which is a mass. You know that. This is mass. Okay. Exponent is 1. Now next we have length. Exponent is a 2. So L 2. Next we have is per second square. It is a denominator. So for denominator you apply what? Negative. So T minus 2. This is a dimension formula. Dimension formula. This was very easy, I know, and we will take more. Next we have power. Power. I think it should be Joule. Joule will come for power. Joule, then watt, watt, or joule per second. SI unit for power is what? SI unit for power is what? For power is a watt, okay? Or you can say joule per second. Here per second is added more. We know that joule, dimension formula for joule is just this. We will write this M, A, but we will stop here because the second is over here. So here 1 is in denominator. So minus 1 and minus 2 will become minus 3. Minus 3, you know, this is complete. M1, L, M1, L2, 3 minus 1. T minus 1. T minus. This is a dimension formula for power, and this is a SI unit. This is a SI unit for power. For power. I hope you are understand. Next we have pressure stress. Yeah, it is new pressure stress. Remember other area. We know that this is mechanics, volume, mechanics, mass density, mechanics, velocity speed for motion, acceleration is for motion, force is for also motion, impulse is also for motion, work and energy is also for motion. But it will link, I think, with mechanics. Power, motion, pressure, stress, I think perhaps, but it will be for mechanics. There are some that are for mechanics, and apart from except those physical quantities that are for mechanics will be here for motion. Now next we have pressure stress. What should be SI unit for this? I think SI unit for this is a Pascal. PA. SI unit, or you can say kg per second per square. kg per second per square. Per means denominator. kg, we have mass m. Either you can say SI unit of a pressure is a Pascal or kg per meter per square. So here m0 not 0, m1 and l1, and t is a minus 2, but here it is minus 1 because of this is a meter, which is a per meter. Okay, this is complete dimension formula. Look at over here. Now I am going to write the next physical quantities of this. Next. Are you ready? No, let me write the next. Okay, next. These are ahead of this, ahead of the 10 physical quantity. Now let's start. Here, look at here. What should be SI unit of first 10? Not a stress of first 10. Tell me. Look at over here. Here, SI unit for this is nothing. Yeah. Unit for this strain, not stress, strain. It is a dimensionless. Okay, it is a dimensionless. There is no SI, no SI. Okay, dimensionless. It means N0, L0 and T0, which means dimensionless. It does not provide dimension. Clear? Still. Next we have modulus of elasticity. Elasticity. It is a part of mechanics. What should be? So for modulus of elasticity is what? Pascal. Pascal. SI unit for this modulus of elasticity is Pascal. Clear? Pascal. And we have same dimension formula for Pascal. But again, we are going to write. So remember, you know that Pascal can be written as kg meter per meter per second as well. Either you can call either you can say that yes, SI unit of this modulus of elasticity is a Pascal or kg per meter per square. Okay, look at here. Kg here mass is 1 and L is 1, but T is a -2. Here it is also -1 because this is a per meter. Clear? Now next we have surface tension. Surface tension. What should be SI unit for this? Unit matters. Okay, unit matters. First of all, you will have to keep remember what is the unit for this physical quantity. Then you will be able to create. Then you will be able to write the dimension formula for those physical quantities. That's why units will matter. So unit for surface tension is what? Newton per meter. Okay, Newton per meter. Newton per meter. Or you can say here Newton is coming, which means Newton is a SI unit of force. Yeah, you know that. So what should be a dimension formula for Newton? You know that M1 L1 T minus 1, not -1, -2, and here we have M also. So M1 L1, but here it is a per. So -1 and 1 will give you 0, and then T is a -2. Clear? This is the dimension formula for surface tension M1 L0 T minus 2. Next we have surface energy. Surface energy is what? SI unit for surface energy is joule per meter cube. Also remember dimension formula of joule. Okay, force as well as joule. Here joule per meter cube. Joule per meter cube. Joule per meter cube. Here you know that it will give you surface unit for surface energy is unit for surface energy is kg per second square, which means m is 1, L is 0 and T is minus 2. T is minus 2. I know that you have confidence to write the dimension formula once you got SI unit for a physical quantity there. M1, M0, T raised to power minus 2. Clear? Now next we have velocity gradient. First of all, we need to know what is the SI unit for velocity gradient. If you know, tell me. Unit of velocity gradient. So it is nothing but per second. Per second. Okay. Per second. Remember, unit of velocity gradient is unit of velocity gradient is a per second, which means it is in denominator. For denominator, what should we do? You know. Here, look at over. M is 0, M is 0. L is also 0, L is also 0. But T is not 0. T is a minus 1. Clear? Minus 1. This is the dimension formula for this velocity gradient. Here, second is a per. Second. Exponent is a minus 1. Now next we have pressure gradient. Pressure gradient. We saw velocity gradient. But what about pressure gradient? For this unit is Pascal per meter. Pascal per meter. Now what is the dimension formula for Pascal? For Pascal, you know that Pascal you just write here over here. 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 So dimension for this is what? This. M1 and here we have minus 1 and here minus 1. So minus 1 will give you minus 2. L is minus 2. Then next we have T. T. T as it minus 2. As it minus 2. This is complete. M1, L minus 2, T minus 2. Next we have pressure energy. Pressure energy. For pressure energy, here energy is coming. Whenever energy will come, you know that what should we do. Here SI unit for this pressure energy is a joule. Joule. And here you know that what should. From this you can write from this dimension you can write a dimension for joule. So here you know that M would be as it. Here L is how much? We have L how much? 3. L is a 2. L is a 2 and T is a minus 2. T is a minus 2. Clear? Now next we have moment of inertia. Moment of inertia. What would be SI unit for moment of inertia? So remember, SI unit for this moment of inertia is just kg into meter square. This kg into meter square is a SI unit for this moment of inertia. Here kg it is a mass You know that this is 1, and here L is a 2, and T is nothing. T is nothing. M1, L2, T0 is a dimension formula for moment of inertia. Next we have what? Angular momentum. Angular momentum, but not angular momentum. We have torque. Next we have torque. So for torque is what? Newton meter. Newton into meter. Newton into meter. For Newton, you know that M1, here we have M1, 1, then L1, so it will give you L2. Then T is T would be as it minus 2. This is M1, L2, T minus 2 is a 4 torque. Next we have rotational kinetic energy. Here energy is coming. Will SI unit be joule for this? Kinetic energy. Yes. Yeah, you are correct. When your energy will come, I think accept this, brother. Accept this. Anywhere energy will come, remember, joule will be for that quantity. Okay. So SI unit for this rotation kinetic energy is joule. And here for this is nothing but just kg per square. Joule. Here this kg per meter square per second square. Kg into kg meter square per second square. Yeah. Kg into meter square per second square. So what should be dimension formula for this? For this, here kg has it. Then we have L. L is a 2. Then T minus 2. Clear? T minus 2. M1, L2, T minus 2. Then next look at a centripetal acceleration. Centripetal. It is related to your gravitational force. Then why did it come here? No, don't worry. Centripetal. But we know that this is also motion. Yeah, it is motion because the acceleration what is added over here. That's why we can say that yes, it is a part of a motion. Clear? So what should be SI unit for this? Yeah, just simple meter per second square, brother. Because acceleration, meter per second square. Clear? Per second square. Now, mass, there is no mass here. So M0, then L is a 1, and T is how much? T is 2. M0, L1, T2 for acceleration. M0, L1, T2. That is how we find dimension formula for all this physical quantity. Did you face any kind of problem? If yes, then you can tell me just by using option. Next I am going to write something else. Something else. Something else. I'm going to write next. This part of mechanics and motion completed. Next will be something different. heat and thermodynamics. Heat and thermodynamics. Look at over here. I took some physical quantities that are for heat and thermodynamics. First is heat energy and internal energy. There is one little bit twist. There is one little bit twist. Twist is that whenever you are observing energy word in the context of a physical quantity, here as you can see, energy word is coming. Now here you need to be crystal clear that is that for this SI unit for this would be just joule, if energy word is coming there. Here look at it, energy word is coming, then you can say SI unit for this is nothing but just joule, clear? Just joule. Here kinetic energy, then joule. Again here potential energy, joule. And latent heat, here energy word is not coming, so joule will not be over here. Joule can be part for this latent heat. Let's write the dimension formula for this kinetic energy, heat energy, potential energy. You know that just m1, L2 and T minus 2. This is the dimension formula. A1, L2, T minus 2. A1, L2, T minus 2 is the dimension formula for this joule. Now next, same m1, L2, T minus 2. Then same m1, L2, T minus 2. This is a homework for you. Now next, what about latent heat? What is the SI unit for this latent heat? For this is nothing but just a joule per kg. Okay, just put joule per kg. joule will be added because of heat is coming. That's all. Joule per kg. Now we know that what is the dimension formula for joule. We know. So m, but here mass minus 1 and 1 will give you 0, and L2 acid and T minus 2 acid. N0 L2 T minus 2. Okay, this is complete till here. This was for heat and thermodynamics. In this we saw something crazy is that uh, whenever energy word is coming, you know that SI unit for that physical quantity would be just a joule. Okay. And for this is what? Joule per kg. N0 L2 T minus 2. Now next I am going to write something different. Something different. I think I need to write separately. These are very important. Wave and quantities, physical quantities that are related to wave and optics will be very important. It cannot be ignored. Quantity. That's all. Now, let's write the dimension formula of each of this physical quantity. Look at over here. First, we have frequency. Frequency just give you second, just a second. That's it. Frequency. Here we are talking about frequency. It is related to wavelength. This frequency is a topic which comes in formula, and in the chapter of human ear, you will say frequency word. So frequency here SI unit for this is per second. What? Per second, which means is raised to power minus 1. Is raised to power minus 1. Clear? So what would be dimension formula for this? M0 L0 but T minus 1. T minus 1. Clear? N0, L0, T minus 1. Now next we have angular frequency. Remember, when your supplementary quantities are coming, just ignore that. Okay, ignore that. Here frequency, but don't ignore frequency. So for angular would be radian, radian, and for frequency you know that what, per second, yeah, radian per second, radian per second. So we will ignore radian, but we this per second will not be ignored. So for per second, m0, l0, t minus 1. Clear? T minus 1. Next we have wavelength. Wavelength. I think it will also provide time. Not time. This is meter. It is a meter. Wavelength. Wavelength. Meter. This is a distance. Yeah. This is a distance. Meter. And frequency gives you second. Time. Time. Within a how much 1 second? Within a how much second? How much wavelength passed? Here, look at here. SI unit for wavelength is meter. We know that. So dimension formula for this would be L0, L1, but T0, T0. Next we have wave number. Wave number. So wave number, for wave number we have just per meter, just per meter, or you can say n raised to power minus 1. Both are same. Both are same. Now look at here. We don't have kg or gram, so m should be 0. Next we have L, which is length. So length is minus 1. T is nothing. So it will be 0. Now next we have refractive index. Refractive index. I think this is a number. Refractive 0.5. Denser, rare. Denser, rare. So yes, it is not. This is a dimensionless. Okay. It gave. This is a dimensionless, which means refractive index. Refractive index we are talking about. This is a dimensionless. So M0, L0, T0. Meaning of this is what? Dimensionless. 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 Clear, brother? Dimensionless. Clear? Okay. Next we have radiant flux. Radiant flux power. So for this is nothing but just watt. Just a watt. Watt. For this nothing but just M1, L2, but it will be minus 3. kg, meter square, and per second cube. Okay, per second cube. Watt, not watt. Now next we have Lumious power. Lumious power or flash. Lumious power. For this Ln, okay, Ln. So for this would be what? M1 and L2, luminous power. L2 and T minus 3. T minus 3. Both are same. For this luminous intensity, it is also same. So remember, one thing is that all these three will be equal. Okay, will be equal. Radiant flux, luminous flux, or luminous intensity. All this will be equal in the order to find the dimension formula. Okay. All these are clear. This was the dimensional formula of some physical quantities. Now I want to tell you about sufficient. Now next we have I hope this is all this are clear. Look at here. I will give you some little bit information regarding the significant number. This is a topic which is coming from this lecture of the lecture named units and measurement. Units and measurement. significant number. Here look at it. We will take any random number. For example, for instance, all this 7, 8, 9, 7.787. Okay, this is we have this number. Now you are understanding importance of a significant number. You are understanding meaning of a significant number in this context, in this lecture. Here we selected this number. Here, if you don't have zero in your number, in that case, all the digits that are in this number will be significant number. So this 1, 2, 3, 4. There are 4 significant numbers. Okay. This is what is meaning. There are some rules, and about those rules we are explaining over here. So first rule is that all non-zero digits will be counted as a significant number. So here 7 is not 0, it is a non-zero. That's why it will be counted as a significant number. Next is 7. So in one number, all the digits are non-zero, so that those will be counted as a significant number. So in this we have 4. In this we have 4 significant figures. Clear? This was one rule. If in a number all the digits are non-zero, will be counted as a significant figure. Now next we have this was one rule. Now next rule. With example, I will explain. 2.0. Look at here. Your focus should be on 0. Look at it. If 0 is coming in your number, but remember decimal. Here 0 is coming, but after decimal here. So any number is coming. First of all, non-zero will be a significant number. So this 2 is a significant number. This is 8, 6, 7. These are significant number. There are 2 points that you need to you can keep remember in your mind, is that if any between two significant numbers, if zeros are coming, then that 0 will be counted as a significant number. But here second is that if zeros are coming but after decimal and these are not ending, then in that case this zeros will be counted as a significant number, including all this 2, 7, 6 are. So finally we have 1, 2, 3, 4, 5, 6. There are 6 significant numbers. So in this case we can say 6 significant figures. Clear? In this we saw that any zero numbers are coming, but after decimal, and then after zeros are coming what? Significant number like this, non-zeros. Then in that case that zeros will be counted as a significant number. Okay. Now next we have 0 adds. Now next rule. Opposite of this. What if 0 is before the decimal? Then in that case what will happen? If 0 is before the decimal, 7, In that case, if 0 is coming in the beginning, zero is coming, then that zero will not be valid for significant number. Okay, and this non-zeros will be valid for significant figures. So here 7, 6, 7, 1, 2, 3, 1, 2, 3. There are three significant figures. Clear? But what about this 0.0? Here 0, there are two zeros which are coming after decimal, and in this we saw that there are zeros coming. If zeros are coming which are after a decimal, then we were counting those zeros as a significant figure. But in this we are also observing that yes, there are two zeros which are coming after decimal. Should we count these zeros as a significant number? I would say no. No. Look at here carefully. If zeros are starting from beginning, in that case all zeros ignore. So here this zero, then zero, then zero. These all zeros together are starting from beginning. That's why these zeros will be ignored to count the significant number. So this is 7, 6, 7. 1, 2, 3. There are three significant numbers. So if 0 is starting from beginning, then those zeros will be what? Will be ignored. But here remember, if there are zeros which are coming between two significant number, then that zeros. Rule is very simple and clear. If zeros are coming between significant number, then those zeros will be counted as a significant number. And here look at here. If zeros are starting from beginning, and in that case, those zeros will be ignored, because in that case all these zeros are starting from the beginning. That's why. In this case, these two zeros are not starting from the beginning. From the beginning, 2 is coming. Okay, 2 is coming at the first place. Clear? Okay, clear. Now next rule let's see. Now one thing more. In this case, we were looking at zeros which are at first position. But what if 7, 6, 7, not 7, 6, 9.00 like that? Okay. In that case, what would you like to say? You would say yes, it should be counted. But look at over here. This is zero. These three zeros are not between two significant numbers. In this, there are significant numbers, but in this side, what about in this side? So here, we cannot say that these are not valid for significant number. No, these are valid. This rule says that if zeros are coming at the end, not at the beginning. Okay, if zeros are coming at the beginning, then in that case, these zeros will be ignored. But zeros here are coming at the end, so these zeros will be counted as a significant number. Clear? So here we have 6 digits, and 6 digits are nothing but 6 significant numbers. So here we have 6 significant number figures. You can do it. So we saw what this one rule. There are non-zero in a number, so all these digits will be counted as a significant number. In the case we saw, second rule is that if between two significant number, zeros are coming, those zeros will be valid for significant number. This was the second rule. Now next, third rule is that if zeros are coming at the starting position, in that case, this starting zeros will be ignored. Clear? This was the third rule. Now next, fourth rule is that Fourth rule is that uh, if zeros are coming at the end, then these zeros will be valid, not will be ignored. Okay. So all these zeros which are coming at the end will be counted as a significant number. Okay. Next rule. For this, right now all these are enough. Yeah. Apart from this, there are more rules. I will discuss all those rules in separate lecture. Right now, that's all.